Hello everybody, my name is Dimitar, and with this video I will try to show you how you can use Monte Carlo simulation for predicting the delivery time for your next project. I will go pretty quickly through the slides and focus on how to simulate project delivery time using Monte Carlo simulation in Microsoft Excel. Clients come to us with an idea for a product and they always ask the questions: how long will it take and how much will it cost us to deliver? They need a delivery date and a budget estimate. But does the customer actually ask for a project? Or is a project just a delivery vehicle or a container for managing risk? We challenge the project management paradigm and suggest it is better to model projects as flow of work items through a system. A project is just a batch taken out from the flow of the work. Say the flow processes thousands of work items. We can name a batch of some 100 work items a project, but we have statistical data for the flow itself and we use that data. Hence the definition. A project is a batch of work items, each one representing independent customer value that must be delivered on or before due date. The batch can contain even only one work item. The size of the work items doesn't matter. There are only two sizes, small enough and too big. Too big should be naturally split by a mature development organization and not allowed to enter the backlog. Here is a simple animation how a batch of work items or a project flow through a Kanban board. Initially, all work items are in the backlog, and then they flow through the board and end up in completed column. This is a cumulative flow diagram from a real project. It visualizes the rate at which the work items were delivered. It also visualizes the flow of the work items through the system. On the x-axis, we have the project time measured in days. On the y-axis, we have the number of work items delivered each day. So the cumulative backlog, cumulative work in process, and cumulative done work items are visualized on this diagram. We will be using the data behind this diagram in order to predict delivery date for future projects. It turns out that the delivery rate, or the throughput, follows a Z-curve pattern as visualized by the red line. The Z-curve can be divided in three parts, or we can say it has three legs. There is empirical evidence that 20% of the time the delivery rate will be slow. That's the first leg of the Z-curve. Then for 60% of the time we will be going faster or be hyper productive. That's the second leg of the Z-curve. And the 20% till the end will go slowly again. That's the third leg of the Z-curve. Of course, numbers may vary depending on the context, but the basic principle about the three sections is correct. Only the second leg of the Z-curve is representative for the development system capability. It shows the common cause variation specific to each dev system process. The first and the third Z-curve legs are project specific and are affected by special cause variation. Examples of special cause variation specific to projects are, for instance, new business domain, which needs to be understood, new technology to be mastered, or new clients' procedures to be used and culture to be accepted. Having seen how the work flows through the system, can we collect some useful metrics that they could help us in planning for new projects? The metric that we'll be looking at today is the Takt Time. Here you can see the formula for the average Takt Time. Average Takt Time is calculated by dividing the time over which the project is delivered by the number of work items delivered. For instance, if we have 20 days delivery time and we have 20 work items delivered, the average takt time will equal 1 day. That would mean that on average the time between two successive deliveries is 1 day. How we measure takt time? In manufacturing, they measure takt time in seconds, in minutes, in hours. In knowledge work, we measure takt time only in days. So what is takt time and how we can measure it? Takt time is the time, as we said, takt time is the time between two successive deliveries. Here is a simple diagram presenting the delivery rate for a fictitious project. Each delivered work item is represented by a yellow box. On the left we have the start date for the project, and on the right we have the end date. We can see that 5 days after the project started, the first work item was delivered. Its takt time then is 5 days. 7 days after that, 2 new work items were delivered. Now, what is their takt time? The first work item has a takt time of 7 days, but the second one has a takt time of 0 days. That is because the time between the two work items is less than a day, and we measure, as we said, time in days. That's why it will be 0 days, although it will not be 0 minutes, but it will be 0 days. Then 2 days after that, 3 new work items were delivered. According to the definition of takt time, one of them will have takt time of 2 days, but the other 2 work items will both have takt time of 0 days. And as we see how it went, eventually all of the work items were delivered. The important thing here is to note that the total sum of all takt time values will equal the delivery time of the project. How this metric actually can help us in planning projects? We can easily calculate the delivery time for a project using this simple formula. So if we know the average takt time for the dev system and we have the number of work items to be delivered, the scope of the project, then we can calculate how much time on average will take the system to deliver all 20 work items. As you can see, the formula is average takt time times the number of work items to be delivered. Here comes the important point. We should not use the average takt time as a single number but a distribution of the average takt time. We shall see shortly how to use Monte Carlo simulation for generating average takt time distributions. So this distribution, actually we will be calling it stochastic information packet, because it is not only the distribution, it is context specific distribution. Every stochastic information packet, or SIP, is unique. It is because we cannot compare one development system historical delivery data with another team. If we do have historical data about average takt time, it will be invalidated if any of the following happens. For instance, team structure is changed, development process is changed, technology being used is changed, development process is changed. For instance, we introduce pair programming. If anything of this changes, all historical data will be invalidated, including the SIP itself. So what is the SIP? The SIP is comprised of a list of trials of some uncertain parameter or metric generated from historical data using Monte Carlo simulation. The technique used is called resampling. The SIP represents an uncertainty as an array of possible outcomes, or said in other words, it's a distribution. And as we say, it is unique per context. It is unique per the business domain, the team, delivery process used, etc., etc. So having the metric to be used and having the concept of as how work flows through the system, we can again ask the question how to predict delivery date. And here is the algorithm to be used. And to be followed. Firstly, we will have to collect takt time data for the development system. Then, using Monte Carlo simulation, we will generate average takt time distribution, or the so-called stochastic information packet, SIP. And this SIP should be stored for a future use. So this SIP will be used for all future projects that will be planning for the same development system. Then when we have the SIP, we can take the third step, which starts when we have a new project to plan. Then we will generate delivery time probability distribution based on the average takt time SIP, again using Monte Carlo simulation. Then when we have the distribution for the predicted delivery time, we will use the 85th percentile as the delivery time that we will be communicating to the customer. The 85th percentile means that for every 6 out of 7 projects we should be able to meet the predicted delivery time. So here is a question that may arise: why not use the lead time per work item instead of takt time for predicting delivery time for a new project? It is because parallel work is difficult to model using only lead time per work item. Imagine the delivery system has 3 developers and they schedule their work as they see fit. At times they may work on 3 work items in parallel. At times the team may work on a single work item. On the other hand, takt time is reciprocal to throughput, is a function of both average lead time per work item and average work in process. Hence, when we are using takt time, we account for both lead time per work item and work in process. Here we will look at a real project as an example, and then we will see how to use Monte Carlo simulation in Excel for predicting delivery date for a new project. So let's open the Excel file. The Excel file can be downloaded. The link to the file can be found in the description section for this video. But first let's look at some advice on how to use the Excel file. I put some notes here. So first note is to change the configuration for about how Excel calculates formulas. So please go to formulas and check manual. That is for avoiding constant recalculation. You can always run a calculation by clicking calculate now for the whole file, or better, calculate sheet, or by hitting F9 button. So let's follow the algorithm presented. First, about the project. It was a project for a Fortune 500 staffing company. It was a software project to develop a recommended jobs engine for them. We possess some statistical data for the supplier organization, for the developers, and we know, for instance, that average takt time for the second leg of the Z-curve was 1.25 days, and we know that the project scope consisted of 27 user stories. Of course, we know more, as we will see shortly, but this is something like a general statistical data. So the first step from our algorithm is to collect takt time data. Let's go better to the Excel. Collection of the takt time data is presented on the sheet throughput takt time. In figure 1, in column done date, the dates when the work items were delivered were populated. If you need to use this Excel file for your own testing and calculation, please insert delete rows from here as needed. So the column count of down is populated with the number of work items delivered at a particular date. For instance, on November 18th, one work item was delivered. On November 28th, 4 work items were delivered. The column takt time will be automatically populated with takt time for that particular date on the particular row. For instance, for the first date when a work item was delivered, the takt time is 4 days. How it is calculated? It is calculated by finding the time between the start of the project and the date when this one item was delivered. So when we subtract the start date of the project from the delivery date, we end up with 4 days as a takt time. And because it's a formula, you can see that each and every row has the same formula, and the takt time is automatically calculated. Then we have to calculate the values of the number of all work items delivered in parallel. It is calculated in column in parallel. Work items delivered in parallel will have takt time of 0 days. For example, if we have as here we have 3 work items delivered on December 1st, then one of them will have takt time of 1 day, and the rest 2 items will have takt time of 0. When we the same formula here, and at the bottom all work items delivered in parallel will be summed up, and actually we end up for here for with 12 work items delivered in parallel. Then we go and create a pivot table here, figure 2, showing the distribution of takt time using the data from figure 1 from this table. So when we change the data in if you want to use this Excel file, if you change the date the number of rows here, please go and update the data source for the pivot table in order the new rows to be reflected in this pivot table. Then in figure 3 we have the takt time distribution with all work items delivered in parallel shown as zeros. So how can we do this? We actually create this table. We will fill it in out manually. So we just copy the values from the pivot table and put it here. Like this column first here, and then this column here. Copy and paste. And then we add a new row, one additional row for all work items delivered in parallel, and we put the number. In our case it will be 12. So we have 12 work items delivered in parallel with takt time of 0, and then we see 4 work items with takt time of 1, and everything to the bottom where we have 1 work item with takt time of 7. So the total of work items is again 27, and the project length is calculated by summing up all takt time values multiplied by the number of work items. Is shown as 43. So here is the formula for calculating the project length, which we know actually because we can easily find it by subtracting the project start date from the project end date. But here, just to validate that if we sum up the takt time multiplied by the number of work items per takt time, we will end up again with the project length. So here we end up with 43 days, which is the correct data. And here we can see the takt time histogram prepared based on the data in table in figure 3. You can see the same, that actually we have 12 work items with 0 takt time, and at the end we have 1 work item with 7 days of takt time. Then we can go and use this data for generating average takt time distribution using Monte Carlo simulation. We will be doing this only for the second leg of the Z-curve, but you can do it for the whole duration of the project as well. So for the second leg of the Z-curve, the calculation is here. For the whole duration of the project, the calculation is on sheet delivery time simulation. They are practically the same formulas, everything is the same. The only difference is that on the for the second leg of the Z-curve, we'll have here only 20 work items, the items delivered during the second leg of the Z-curve, and for the whole duration of the project, here we have 27 work items, so the full scope of the project. So let's go to the sheet Z-curve second leg time simulation. And here, as we said before, all rows or cells that which should be populated with data are highlighted in yellow. Everything else contains formulas, and it should not be changed. Of course, if you prepare your own Excel file based on the approach presented here, of course you can make it different and most probably prettier and better. But here for this video, we will change no formulas. So here in cells B3 till B22, we populate the historical takt time data that we collected here. How we do this? We just take the takt time data from here, from column D, copy it, go to the Z-curve sheet and paste it here. We should add also all takt time for all work items delivered in parallel, which for the Z-curve we have 9 such work items, and for them we just add 9 times the 0. And again you can see we have 20 work items, and we have the takt time for all of them. So the method for the technique that we'll be using for the Monte Carlo is called resampling. What actually it does is for every takt time entry in this table, Excel will run this particular formula. What the formula does is to choose at random one of these 20 values of historical takt time data. It is done by first using the Excel index function, and then using the function run between. So what it does is run between will generate random numbers in the interval of between 1 and in this case 20. It is because we have 20 work items. So Excel will generate a random position in this list here, and then the index function will populate in this particular cell the value randomly selected value, and we do it for all 20 work items, and eventually we end up with a random sample of the initial historical pool of takt time data. We can see how it works really fast here. We go to formulas and we say calculate sheet. So please look here how the values will change. So say calculate sheet, and you see how the values are always changing. Of course it calculates everything else on the sheet, but first we will focus on this column. So Excel upon every calculation will just create a new sample from the historical takt time data. Then using the built-in data table functionality in Excel, which is here, we can run this particular resampling many times. In this case I put 1,000 runs of the same sampling. On top of that, we will not just resample the data, but we would like to use the randomly generated sample for calculating delivery time using this formula. So the data table works in a way that here we have the formula which will sum up all these values. All these values will be summed up, and the result will be put here. in the respective column. So we have 1000 items, right, 1000 runs, and Excel automatically will first generate a random sample, then sum up all of the takt time data, and as we know, the sum of all takt time data will give us the total length of the project, and it will end up here, populated 1000 times. And here in the next column G, we will calculate for each random delivery time. We will calculate the average takt time using the formula as we saw before, which is like we divide the delivery time by the number of items here, which is always 20 in our case, and we end up with a different random value for average takt time. So again, I will hit the calculate sheet, and you can see how the delivery time column values will change and average takt time values will change. So let's see again. Just waiting, it's the calculation, and you can see how values are constantly changing again. So it is done 1000 times. Then here in this table we have the histogram for all the data, the values in the data table. This particular histogram is for the delivery time. So we create the bins here. This is the delivery time is in a range, and here it is from 4 days to 50 days. That's the maximum values we have in column F. And then using the Excel frequency formula, we actually end up with the frequency of each value. Based on the frequency, we calculate the probability density function and the cumulative density function, and we show them here on this diagram, and we can see how it works in real time. Yeah, again, calculate sheet. You see how the diagram actually is changing. Every time I hit calculate sheet, Excel runs 1000 times, simulates delivery of this particular type of project. Here we have some descriptive statistics for the data, for the simulated data. We have the median, standard deviation is just in case, the average delivery time, the 85th percentile, the 95th percentile, and the mode and the size of the sample. As we said, here in the data table we have 1000 runs. What is interesting is that actually the mode is less than the mean, which is less than the average. This is very specific and like a characteristic for the Weibull distribution. And shortly we will see how actually we will prove that this data here, the simulated data and the data presented on this diagram, is Weibull distributed. So this is the again for the simulated delivery time, and down we have the same but for the simulated average takt time. Again, average takt time is calculated here in this column, and we have the same frequency calculated. The bins, the range is from 0.4 to 2.3 days. We have the frequency here, and then we have the PDF and the CDF, and they are presented here. Again, if we go and check that the descriptive statistic for this for the simulated data, we can see that the mode is less than the median, which is again less than the average. Again, very much like a viable distribution. So how can we check if the delivery time data is viable distributed? On the next slide, which is next sheet, which is a Z-curve second leg time viable fit, we have actually checked how it works, and it's really simple. We go here and copy all the data from the column C, all 1000 simulated deliveries. We paste it here, then we order it by using Excel sort and filter, and we say sort smallest to largest, and here please select continue with the current selection, and it will sort only the selected column, and we end up with this data, which actually show us that if it was a viable distribution, the predicted mean is really close to the actual mean from the values, and we end up with the shade parameter of 4.47 and a scale parameter of 27.66, and you see that the correlation is really good, almost 1, which actually proves that the data here, the simulated delivery time data, is viable distributed. And this sheet and the data in these two columns, and especially in the column G, represents our stochastic information packet. What we should do is just store this particular sheet somewhere, and whenever our dev system receives a request for a new project and there are no changes and the statistics will hold, and there is no change in the development process, in the domain, etc., as we saw before, we can use this data here in this column average takt time for predicting how much time will take us to deliver, let's say, 100 work items. Remember, this project actually has a scope of 27 work items. So what would happen if we receive a new project with 100 work items to be delivered? So then we go to the sheet called projected for n work items. Again, the cells highlighted in yellow are the ones that can be populated with data. And here, what we will be populating? We will populate the project scope, which in this case is 100 work items. Here we will populate the data from our SIP, which is for average takt time, which again is really easy to get by copying all the values from here to this column. Again, there are 1000 values, and we will be running a simulation of 100 runs. So again, our goal is to predict a delivery time for 100 work items for the same development system, the same team, the same business domain, the same development process used. Here, just for convenience, we see the distribution of the data in this column, the average takt time data, which of course is similar to the one here. To the one here, because it's the same data, right? It is just for convenience. Let's imagine that actually this is a new Excel file only for planning the new project, and we just copy the data for the average takt time data from the SIP which we have stored somewhere. So we copy it here, and then we want to simulate again, run a Monte Carlo simulation for the new project. We will be using the same approach as before. Again here in the we will put just a simple table here, and we use the index function and the run between function. So for every entry in column C, we will be randomly generating generating a position, and take the value for this the generated position, and multiply the value by B3. In this case it holds the number of work items. So again, what we are doing, let's just go through the presentation. Yeah, the historical time data. Yeah, so we are here, generate delivery time probability distribution, and this is the result. And the formula, just to recall, the formula is as follows. See, this is how we calculate delivery time for a project. We take the number of work items n and the average takt time tt, and we calculate the delivery time. But here we are not using only the mean value of the takt time. We are simulating 1,000 runs with different values for the takt time. The values for the takt times are here again. And using the formula, you see we end up with a different values for the delivery time. How can we calculate this? We go again here, we say calculate now, but only calculate sheet. We run it, and you see that the values are changing. This sheet is not that heavy in terms of calculation, so it's faster. And where we can see the results, we just scroll down, and we see here the frequency of these values. The range from 40 to 220 days. This is in days. The frequency again, the PDF and CDF, and here we see the histogram and the CDF on the diagram. And again, let's calculate. You see how the diagram actually is changing constantly, because we are simulating every hit on calculate sheet runs 1,000 simulation of this delivery of the project. And you can, well, we can take as advised in my presentation to use the 85th percentile, which in this case will be 165 days. Again, just to mention this this delivery time data, the projected delivery time, again is variable distributed. You can check it here again, the same way as before, and we end up with the delivery time, the projected delivery time for our new project. The interesting thing here is what will happen if we have only one work item to deliver. Let's say that we are not delivering projects, we are servicing item by item. Let's see what will happen. Let's put here one. The project scope is one work item, and click calculate sheet, and you can see that for one work item it will take, based on our historical data, between the ranges between 0.4 days till 2.3 days, with the 85th percentile of 1.6 days. What is interesting here is that the data is again, the result is again variably distributed, which is here to prove that the lead time, because when we have work a scope of one work item, the lead time for this per work item will equal the lead time, the delivery time for the project, which means that in this case we simulated the lead time for a one item flowing through our system, it is again viable distributed. Again, the file, this Monte Carlo simulation file, can be downloaded here, and also it is in the description of this video. And also I would like to thank and give credit to several people. The content here is inspired and based on ideas from David J. Anderson, Troy McGinnis, and Alexei Zheglov. To close this video, the approach presented can be used for any kind of development process, including Scrum, Kanban. Any kind of process can be simulated using the approach presented. I hope you will take your own historical data, put it in the Excel file, change it accordingly. I mean, if you have more than 20 work items or 27 or whatever, and run it 1,000 times or more, and start planning your future projects using probabilistic management. Thank you very much for your attention.